In this lesson we'll be discussing polytropic processes. So polytropic processes we define as a process that obeys the relationship pressure times the volume raised to eta is equal to a constant. Okay, and when we talk about eta, eta is what we call the polytropic process exponent. So there are special processes that obey this relationship, which really mean that we can then write the equation that if we're looking at a process goes from one state to another, we look at going from state 1 to state 2, then for a polytropic process, pressure 1 times volume 1 raised to the eta is equal to pressure 2 times volume 2 raised to eta. Now all of this may seem a little bizarre and obscure. It makes more sense when we start looking at special cases of eta. Okay, so we'll start talking about that now. So the first special case of eta we'll talk about if eta were equal to 0. So let's look at that. If eta equals 0, then our equation becomes pressure 1 times volume 1 raised to 0 is equal to pressure 2 times volume 2 raised to 0. Well, anything raised to the 0 power is always going to be just 1. So then this equation simplifies back down then to pressure 1 is equal to pressure 2. If pressure 1 is equal to pressure 2 during a process, we have a special phrase for that. We call it isobaric, which means that it is constant pressure during that process. So if eta is equal to 0, that is a polytropic process, which is isobaric. All right. Another special case we'll look at is if eta were to equal infinity. So then we have pressure 1 times volume 1 to infinity is equal to pressure 2 times volume 2 to infinity. Now, this one is a little more confusing. It's not as easy to see what's happening here. So we're going to rearrange this equation, putting pressures on one side and the volumes on another. So now we have pressure 1 over pressure 2 is equal to the quantity of volume 2 over volume 1 raised to infinity. Still, I'm not really sure how this is going to change. So now what we're going to do is, what if we were to raise it by both sides by 1 over infinity? Well then, the pressure side would be raised to 1 over infinity. The volume side would be infinity over infinity. It would balance out, so it would just be the volume relationship. Well, so we get that the pressure 1 over pressure 2 raised to 1 over infinity is equal to volume 2 over volume 1. 1 over infinity, if we have 1 divided by the largest number possible, well, that's going to give us 0. And again, anything raised to 0 just is 1. So that means that the relationship of volume 2 over volume 1 equals 1. Well, that's the same as saying volume 2 is equal to volume 1. So then we can say that when we have eta is equal to infinity, we have a isometric process. Remember, isometric being constant volume, also known as isochoric to some circles, but we're going to stick to isometric in this class. So constant volume. A third case that we might see, eta equals 1. All right? So now we just raise it to the 1. We might as well not even have that raised to the 1. But let's look at the original form of the equation where you say that pressure times volume raised to the 1, it's going to be volume, is equal to a constant. Where might we have seen that before? Well, let's think back to the ideal gas, right? Ideal gas law, pressure times volume is equal to the mass times that universal gas constant over the molecular weight times the temperature. Well, that side's not necessarily constant, but if we say it's a closed system, right, ideal gas, and if the universal gas constant is going to be constant, the molecular weight's constant, well, if the temperature were to be constant, then all of a sudden we would have a constant process, and then all of a sudden the right side of this equation would be constant. So if eta is equal to 1, what we then say is that we have a isothermal process for an ideal gas. Isothermal being the temperature does not change. So, if eta is equal to 1, then we can say that we have a isothermal process. The last one we're going to talk about is if it's equal to K. Now, we haven't done a lot with K recently. We know that it's the specific heat ratio. But we know from this is it tells us that, I'm just going to give you that it's isentropic for an ideal gas. Now, we haven't dealt with we haven't dealt with entropy yet. And we likely won't get into isentropic relationships, but this is just good to know because this is kind of a thermodynamic known fact that for polytropic processes, if we make A to K, then we have an isentropic process for an ideal gas. So these are the 4 special cases you should know for a polytropic process.